We will go ahead and get started then. This is actually sort of wrapping up the material that we talked about last week and then setting up the next stuff. So it's kind of a transitional lecture. And we'll start getting into the meat of some pretty exciting stuff on Wednesday and Friday as we start talking about SQL queries, how we turn them into plans, and all of the nuances and the vagaries about how we might execute these things and translate them into stuff that runs more efficiently. So we'll start talking about that. So today shouldn't be too long of a lecture. Yeah, we finished talking about, remember we talked about various levels of organization that we can have in our tuple files, our data files. Remember we're talking about relational databases. So if you're wondering about graphs or how to store XML so that you can process it efficiently, or key value stores, not really the focus of this term. But anyway, we talked about block level organization so that we could, for example, find a block to put a tuple in efficiently so that we don't have to search through the entire file. But we can also organize files at the record level, which turns out to be relatively common and gives you some big benefits. And I mentioned this last term that we have basically the most common file organization is the heap file organization, which basically imposes no constraints whatsoever on where a tuple might appear in a data file. So like I say, a very simple little additional structure. Basically, we can have block level structure if we want to improve efficiency, but as far as record level structure, we have none. It's very simple. Virtually all of our disk blocks in our data file are treated the same. They all contain tuples, and it's very simple. And like I say here, it is the most common file organization. It wasn't always, because we didn't always have good ways of processing data efficiently. And so there were a few others that were a little bit more common. Another organization is the sequential file organization. Basically what you're doing is you're saying that tuples are going to be in some sequential order, okay, based on this thing called a search key. And I mentioned that last time. And then you could also have hashing file organizations where the records are hashed and you can use some hash key to figure out approximately more or less where to look in the data file to find the record that you're looking for. Okay? So these are three different organizations. And then we also have this fourth one, which I've mentioned from time to time, multi-table clustering file organization, which is helpful on a magnetic disk because you can co-locate records that would be joined together from different tables, and that should improve your equijoin performance. Remembering that an equijoin is a join on an equality condition. We will definitely be talking about that a lot in a week or so. Okay? So these are four basic, very common file organizations, and there's certainly databases that do all of these things. And like I was saying, back in the day, before we had really good join algorithms and so forth, before we could construct indexes on the fly against data that we just generated, it made a lot of sense to actually take the hit and use a sequential file or something like that, because that would allow us to do more efficient joins. And doing a heap file organization wouldn't help us very much. So as time has progressed and our sophistication level has progressed in managing data, we've migrated to the point where everybody basically uses heap files, and then we build indexes against them. Now, sequential files, they're organized based on some search key. And, of course, we could have a couple of different circumstances. We could have a situation where we have a query involving the search key. Those are the days that make us happy, because then we can actually take advantage of our sequential file organization. Like I say here, a sequential scan of the file is going to give us the records in sorted order, so we don't need to do anything in addition to generate sorted output. So for example, if we have a query that says I want to order by the search key or some prefix of the search key, then I'm happy. I don't have to do any sorting. It's already sorted in the data file. Or if I do a query and I say I want to find a record with some value in it that is a value of the search key, then maybe I can do a binary search or some kind of search where I can greatly reduce the range of the data file that I need to look for. And if I can do that, then I can also do range-based queries very efficiently, like I have here. I want to find all the values that fall within a range. Well, I start finding records with the lower bound. I try to find that efficiently, and then I can just scan through the sequential file to find the remainder of the records that fall inside the range. So sequential files give us a lot of big benefits, and we really like having sequential ordering because it turns out to be the most generally useful organizational method for data files to improve the efficiency of queries. And like I say here, there's also implementations we can think about. Remember I said before, all of our algorithms, all of our data processing generally falls into one of three categories. The general category, the category where the data is sorted, and the category where the data is hashed. So those are going to be, you're going to see those over and over and over again. So we have more efficient implementations for joins, grouping and aggregation. If we want to group and aggregate on a data file that is in sequential order and we want to group on the search key attributes, well, we just iterate until we see the values of the search key attributes change. And then that tells us the next group has started and so forth. Okay, so various things like that become very easy with sequential files. Now, what if we're not accessing based on the search key? Do we get any benefit from the fact that it's in sequential order? The answer is no. And this is kind of, again, a common reality that you will see throughout. We have to support heap file type record files anyway, because there's not every one of our accesses is going to be based on the search key. And so a lot of times we have to traverse these things anyway. Okay? So records are in no specific order. We have to traverse it just as we would for a heap file. Okay, well that's fine because we can figure out what are our common access patterns and create sequential files with search keys that make sense, and then we can take advantage of this in our databases. You guys are already familiar with this because we had to figure out, well, where did it make sense to put indexes? We didn't want to just create every possible index because that would be slow. But you look at what you're doing against the data and say, okay, it makes sense in these situations to create indexes. Okay, so search keys can contain multiple columns, and again, I think you're all familiar with this. So let's say we have a table T with 4 columns in them, and the search key is on the first 3 columns, A, B, and C. And so what we mean when we say we have a multi-column search key is that the rows are ordered based on the first column's values, and then within ranges of the first column's values, where the values are actually equal, we order on the second column's values, and so forth, just as if you were sorting data alphabetically or something like that. So if you have a table that's sorted on A, B, and C, then it's also sorted on A, and it's also sorted on A and B, which means that if, again, we had this table T and we wanted to do a grouping and aggregation, and the grouping attribute was A, or the grouping attributes were A and B, we're still happy. We can still do that in a sort-based grouping and aggregation operation as opposed to just a hash-based grouping and aggregation, okay? Which actually has a much smaller memory footprint than a hash-based grouping and aggregation. Same thing if we want to eliminate duplicates based on A or based on A and B, we're good. Okay. Now, what if we wanted to do a grouping and aggregation based on B or on B and C or on C? There might be some way to maybe take advantage of it. But the further away you get from the start of the search key, the harder it is to take advantage of. Because you know that within each one of these, distinct values of A, B, C, that, or I should say, let's take C for example. So within runs of A's and B, the C's will be in order. But we don't know how many runs there may be. There may be many, many runs. It may be more efficient to just take them and sort them based on C, rather than trying to do something clever with the sequential file. So you have to be careful because when you try to be, there's this whole thing like you can end up being too clever for your own good. Like suddenly, you would do just as well, pulling in runs of data and sorting it in memory and then writing it out and so forth, as opposed to just trying to be clever with the data file. Okay, sequential order. So how do we maintain this? And we're not going to talk about this in very great detail right now because hopefully you already know the punchline, because the real answer is B trees, and we'll talk about them in great depth in the future. But we have these various things that we need to think about. How would we insert records into the sequential file? What about deleting records? Because if we delete records, that frees up space, and then we could insert new records, but should we use that? Because will it actually be in the right position, and so forth. There's a fundamental rule, and again, we're talking about data structures that exist on the disk, so we can't really reorganize the entire file every single time. So what we'll do for now, just as a really simple approach, is to just add a little record pointer to each tuple. Okay? And we can do this in databases. We can say, okay, the user said, I want to create a table with these 4 columns, but I, as the database, am going to go in and add in a few extra columns just for my bookkeeping. That's certainly a common thing that database systems can do. And so we might have something like this. So we have our accounts ordered by branch name. And right now we're happy because our logical ordering of our records also matches our physical layout of the file. Again, we're speaking in the context of magnetic disks because solid-state drives don't really care about the order, right? Because there's no seat time. But with magnetic disks, there is, and so initially we're happy because scanning through things in logical record order is going to also scan through things in physical order, and that's going to yield an efficient access. So when we add new records, we need to think about, okay, where does it go? And ideally, we would be clever and leave a little bit of space in each block so that we could add some number of records in their appropriate locations without incurring a huge performance hit. That would be the smartest thing to do. I've mentioned it over and over again that it tends to be in real life that time is more expensive than space. It's cheaper to go buy a new disk and stuff it into your system so that you have more space than it is to try to engineer things better or to waste the time reorganizing things frequently. Just throw more space at it. So anyway, if we don't have space in the data file in line, then we go ahead and just append the record, and we'll have the pointers keep things in logical order. So we might have a situation like this. Okay. That's a simple one, right? Probably this still all fits in a disk block, because if you think about how big each one of these IDs is and how big each one of these branch name strings is and the balance, we're probably talking like, what are we talking? Maybe 30 bytes, 40 bytes per record right now. You could cram a lot of those into a 4 kilobyte or an 8 kilobyte block. So this wouldn't be bad because our logical order and our physical order are still basically the same. But over time, you could imagine that we could have a really nasty rat's nest of record pointers that completely deviates from the actual physical layout. Okay, so this is basically what I was saying before. And it turns out, again, if you're familiar with B trees, that this is in fact what we have to do. We have to maintain some extra space in disk blocks so that file reorganization is as infrequent as possible. And we actually do this with hashing file layouts as well. Okay, but like it says here, after many inserts and deletes, it will eventually become disorganized unless you're doing some kind of periodic maintenance. Okay. And yeah, the fundamental issue is just this whole disk seek issue. Now, there are always solutions. You could pull the data into memory as much as you could and then just follow the record pointers in memory. And that would certainly be a solution. But the problem is that we're talking about data that isn't going to fit entirely in memory. And that's one of the nice things. I think it's nice, but you may not think it's nice for very long. But one of the nice things about NanoDB is you can actually, there's a knob that you can use to control how much data is, or how much space is available for data in memory. The buffer manager controls all allocations in NanoDB. And so we can crank it down, even though you might have 2 gigs of space, we can crank it down to like, well, you can have 100 kilobytes of space for reading in records and so forth, so that you can see how this kind of stuff works. So we do need to periodically reorganize files. And again, this is what B trees do. They do periodic reorganization. You can still have issues that occur with block level structure not matching physical layout. But you can be clever about when you do this so that you try to avoid imposing performance impact on queries. Okay. Now, are there any questions about sequential files? Again, this is just to give you a high-level sense of some of the issues that you might encounter with this. The interesting thing is this whole record pointer thing might actually be an interesting approach with solid-state drives. B-trees require you to change data structures in place a lot. So you might, again, for 123, think about, well, I might explore coming up with an alternate sequential file format that works really well with solid-state drives. So that would be something interesting to think about. Okay, hashing file organization. So we have hash keys instead of search keys for hashing file organizations. And again, if we have an access that is using the hash key, then we're happy because we can do that lookup hopefully in constant time. Okay, but we'll discover that there's some challenges that we run into relatively quickly with hashing file organizations. But you'll notice here that I say you cannot really use hashing file organizations for range queries or inequality queries and so forth. And so this is the big reason why hash files are actually far less common than sequential files in database systems. Because you can get so good with sequential files that it's only slightly less expensive than hash files, and you can also do range queries with them. Whereas with hash files, yeah, they may be slightly faster for lookups based on equality, but you don't also get other benefits from them. So this is why hashing file organizations tend to be relatively uncommon with database systems. It tends to be databases that do these things will support these as in-memory tables, in-memory only, as opposed to on the disk, because there's just too many downsides. Okay, so that's just a general overview of this, but hopefully this all makes sense to you. If you're not accessing based on the hash key, then again, basically treat the records as in no particular order. And so it's no different from accessing a heap file. Hash keys can contain multiple columns. That would definitely make sense in certain circumstances, but you'll notice that if I have a hash key with multiple columns, that's not useful for subsets of the columns. Unless you come up with some very, very clever way of hashing things, which I suppose you could, but in general, people don't. People just hash into a single value to figure out what bin things go in, and they take it from there. So having a subset of the columns in a query or something like that doesn't really help you with a hash file. You still have to scan it. Okay? Any questions on this? Okie dokie. So that's a general overview of that. So in-memory hash tables. Who here has implemented hash tables? Please, people, have you implemented? Yes. Okay, awesome. Makes me so happy. We have a future. So what are the two basic ways of doing hash tables? Does anybody remember these things? It wouldn't offend me if you don't remember the names for these things. But there's basically two ways of doing hash tables in memory. Yeah, so hash function is going to be part of it, but what do you do with the hash function? Yeah. Sure, you can have buckets with linked lists. Why do you have linked lists? Yeah, so we have hash collisions, and that can... So you have buckets with linked lists. That's one way of doing it. Does anybody know another way of doing it? Hint, it's the way Python dictionaries work. No trees. We're not allowing trees in this situation. Hashing, it must be hashing. No ordering. Anybody remember? The other one is called open addressing. Has anybody heard that term before? Open addressing. So instead of having some small number of bins, and if you have a collision, then you have a linked list inside the bin, you just have a whole series of slots. And the hash function basically tells you what slot you'd like to put the value in. But there may be a problem in that there's something already in the slot. So you just start scanning linearly through the hash table until you find an open slot, and then you put it in there. That's called open addressing. If you hit the end, you wrap around. Ideally, you don't wrap all the way around, then the hash table's full. Good hash tables keep track of when they're starting to get full, and then what do we do if we start to notice that things aren't going well in general? Yeah, so we make it larger. What do we do? Somebody tell me, like with bins, what do we do? We say, okay, 8 bins is not good. We have some definition of what is good or not good, and then what do we do? Yeah. Yeah, you double the number of bins, and then what do you do after that? What do I rehash? The answer is everything. Right? So that's the challenge. Now, and the same thing is true of open addressing. I create a new set of slots that's maybe twice as large or something like that, and then I rehash everything. And that's kind of the nice thing about when you're working in memory, because you can rehash everything. It's okay. But anyway, those are the two basic ways of doing it. So bins with chaining or open addressing. And so we have to reorganize things. Here's the question. How do we do this in a data file? Let's say that we want to manage a hashing data structure in a data file. Because we can't rearrange the entire file. At least not without imposing a huge performance. I mean, think about if I have, and it'd probably be dumb to do this, but let's say that we had like a 10 gigabyte data file that was in a hash file organization. 10 gigs. And I discover that I have too few bins. Because I'm using that approach. Well, then I need to increase the number of bins and create a new data file with all the record organizations, or record positions, I should say, updated to be in the appropriate locations. But I have to rehash the entire data file. That's expensive. So we don't want to do that. But we're not going to talk about how to do this right now, because we're going to talk about indexes later. We don't want to get ahead of the story. So what we'll do is we're going to have a very simple approach that we use. Like I have here, it's called static hashing. And you'll probably cry a little bit when you're like, no, it could be better. And it can be. We won't talk about dynamic hashing until the future. But open addressing isn't great because we have to scan through the entire data file, and that's slow. So we tend to fall back to bins or buckets, as I have on the slide. Bins with a linked list of pages that are in each bin. And that would be static hashing. So we have a fixed number. And this is where, again, you take a guess as to how many bins you might need, and you hope you guess right. And also, like I say, you have different ways of representing this. We'll have a very simple way of doing it. We'll have each bucket will be a linked list of disk blocks in the data file. And or like I have here, you could have n sequential disk blocks. Although, with the tuple sizes we're talking about, you can cram hundreds of tuples into each page. So a single disk block would probably be fine for now. And so we'll have some hash key, so some set of attributes in the tuple file that's mapped to a bucket B with some hash function. And that's really simple. I mean, typically what you do is you have some hash function, and you take that modulo the number of buckets, and that's really simple, and you can use that. And then each record goes into the corresponding bucket. We do need some way of saying this is the mapping, so we can store that in block 0. Like I said before, block 0 is going to be special throughout the entire term. Is that right? Yeah, maybe write-ahead log files are not special, don't have a special block 0, but everything else does. Block 0 will always be where you squirrel away important information about the data file. So you could have a sequence of buckets, and notice here that buckets 0 and 2 exist, and buckets 1 and 3 have not been allocated yet because they still have 0 for the block number in the mapping. And so if the bucket holds records, we'll have a non-zero block number, and in that block we'll just have a sequence of records. We could store them with, let's say, our slotted page organization. That would certainly work. Okay. And so, yeah, we assign blocks to buckets as we need. Now, at some point, we get into a situation where a bucket has a full block. And this, again, happens. It probably won't happen after 3 records unless your records are multiple kilobytes in size. You could certainly do this. You could do this in NanoDB because it supports varchar up to 64K, at least as a concept. And so you could easily fill up a bucket. And so you have to overflow records now into a new block. And so you can see now that block 1 and 3 are both part of bucket 2. And the entry in block 0 just tells us where the bucket's contents start. Okay, so we could have linked chains of blocks as before. Of course, you have this interesting thing. Well, what if I deleted records 2.1 and 2.2? Do I want to leave that space, or do I want to try to reclaim it? Do I want to try to reorganize things right away? So you'd have these kinds of questions that you'd have to sort out. And so you can imagine that designing a file system data structure is not hard, but designing one that's efficient and responds effectively doesn't use a lot of space, and doesn't take a lot of time in general usage patterns, that's what makes it challenging. Because what I would probably do is say, okay, bucket 2, like the start of my bucket would have like the last block in the bucket as well as the next block in the bucket. And that way, if I do delete records, I can go ahead and relocate records from the end of the sequence so that maybe I can free up a block or something like that. I would probably try to do something like that. Anyway, but these are some things that you can think about. This is a very simple approach. Are there any questions? Okay. Now, again, a great project idea for 123 would be to implement the 3 different kinds of hashing files that we will talk about in 122 and see which ones are good and which ones aren't good. So it would be an interesting thing to do. Okay, now there are some limitations. What is an obvious limitation of static hashing, as I've described it here? Remember, we have this whole guarantee that hash tables give us. Constant time lookups, right? How do we have constant time lookups? Yeah. Yeah, we basically make sure that each bucket stays below some constant fill size. Can I do that here? Not really. I have a fixed number of buckets. Static hashing is, it is technically hashing, but we don't have the benefit of hash tables anymore. Because lookups will get slower and slower as our data file gets larger and larger. Okay, so that's one obvious issue. What's a less obvious issue? Now, there's another consequence. Again, let's stick with bins and overflow lists and so forth. If I have that approach for hashing in memory, what's my ideal? Like, ideally, my hash function will map all of its values to different bins, right? I'll get a uniform distribution. So what could happen? Yeah. Yeah, so what specifically? Yeah, so we definitely can have that problem with static hashing. In memory, we're cool in that if any bucket gets over full, we can rehash. So that's nice because then our hashing system sort of adjusts to the distribution of the data that we're hashing in general. Okay? So if we don't have a uniform distribution of hash values, then presumably we will have some buckets that are really empty, and that's a little bit of a waste, but we don't mind. And we have other buckets that we're still keeping under our maximum limit of contents, but we can keep breaking them down. We can't do that with static hashing. So if we have, so I have this situation. If we have a situation where there's not good distribution of hash values, static hashing is going to behave terribly. So, and I mean, basically what you're going to have is you'll hash to get to the appropriate subset of the records, but then that may be the bulk of the records in the table, and now you have to scan through them linearly again, which is kind of annoying. Not to mention that you have this linked list, and what can happen with the linked list? It's on a disk. The logical order may not match the physical order, and now I'm incurring a whole bunch of disk seats. Okay. Now, just as a little hint, there's always tricks. There's always ways around this. So I'm going to throw this out now, just because I think it's so cool. I can't keep it a secret. But imagine you did have a situation where you have a hash table using static hashing, and you have an overflow bucket, or a sequence of overflow buckets that are really large. Now, obviously, if you allocate data in these files in chunks of blocks, like multiples of 4 blocks, then your linked list gets shorter, and things will be more linear, so that's always nice. That's one approach. But the other approach is you could always read the linked list elements, the block numbers, into memory, and then you could sort them and then read them off the disk. So you always have little tricks like that you can do that will allow you to do less disk seeking. Now, in this situation, it probably wouldn't help you, but there are definitely situations where it will, and we'll talk about those kinds of tricks in the future. But just keep in mind, there's always little techniques you can use to make things faster. And that's why database implementations get complicated, because of all these little tricks. Okay, so we would prefer a dynamic hashing mechanism, like what we use in real life. I should say in memory, but we'll talk about that in the future. There turn out to be two really cool and clever dynamic hashing mechanisms that you can use to create these hash files and have them balance over time so that buckets can get split or the number of buckets can be increased in clever ways. So we'll talk about that in the future. Okay, so any questions about static hashing? All right, so that's that. So you can see that the simplest file organization is heap files. We don't need any more additional record level organization. And since the other things have to have this as a fallback case anyway, why not just do heap files initially? And we can have improved performance from these other file organizations, but people tend not to do that. People tend to use heap files, and then we use these other file organizations to build indexes. Okay? Yeah, we talked about this as well. The real problem with magnetic disks is when the physical and the logical organization don't match. That's when it becomes very, very slow. Okay, and let's see. Most common solution we're all familiar with. Store the records themselves in a heap file. We build indexes against the heap file using some alternate storage method. Okay, so we can use a sequential file to store an index. We can use a heap file, or a hash file, I'm sorry, to store an index. And then we can use that to index into the heap file. So we'll talk about that in the future. And then the index gives us all kinds of opportunities to start optimizing our queries. Okay, yeah. Any questions at this point? All right. So yeah, we're evaluating queries, so we'll just talk about this. Next thing I want to talk about, this is another classification which I probably should have incorporated into last lecture, but I do need to mention it, is sometimes when you're reading database literature, you'll see these terms internal memory versus external memory. And I wanted to make sure to explain these as well, because we're going to start using these terms as we talk about various things. External memory duplicate elimination, external memory sorting, and so forth. So we had this storage hierarchy: primary storage, DRAM, your caches, your registers, if you technically, they technically are memory. Secondary or online storage, your flash memory, solid-state drives, hard disks, and then tertiary storage, offline or nearline storage, would tend to be your tapes, presuming that the tape is sitting on a desk or on a shelf somewhere and not in the tape drive, or your optical media. And of course, we're all familiar with writing programs that work with data in memory. I'm sure all of you have probably written programs that work with data files. What do? You load the entire data file into memory, and then you process it, right? And then when you're done, you write back to disk somehow. Okay? It tends to be relatively uncommon to interact with data files on an ongoing basis to process the contents of them, unless you're doing things like processing, maybe mining large amounts of data. And since databases work with data sets that frequently are larger than memory, then we need to think about how the algorithms will work with not just primary storage, but also secondary storage. And this is sort of the whole distinction that I want to show you here. Basically, you have external memory algorithms. It's a whole category of algorithms that you typically see discussed extensively in database systems. External memory algorithms use both our DRAM, our primary storage, and our secondary storage. Okay? And so we have these other terms that are sometimes used. Internal memory is primary storage. External memory is secondary storage. Like, I don't know if any of you are avid C++ programmers, but if you are, you're probably familiar with the STL, Standard Template Library, and the C++ Standard Library. There's a version of the standard library called STXXL, referencing the XXL, like 2XL shirt size. STXXL is a version of the standard template library that can use external memory. And so if you need to work with data sets much larger than memory, you can use STXXL to work with that data effectively. Okay? But anyway, like I have your hash file organization, or dynamic hashing is sometimes called external hashing, because it involves a disk as well as data in memory. And so just be aware of that. There's a lot of interesting algorithms that you can find if you get on the ACM digital library and look for external memory algorithms and so forth. Okay, we'll talk about external memory sorting, for example. How do you sort data sets that are much larger than your primary storage? Okay, so I just want to make sure that you're familiar with that term because we will encounter it. Now we'll go ahead and start talking about query evaluation. Are there any questions to this point? Okay, so just you can go ahead and start this topic now. So SQL is the language that we generally are stuck with. You could probably imagine much better query languages, but SQL somehow is caught on, and so we're going to talk about how to execute that. The one thing is that most databases don't actually try to interpret SQL, because that would be horrible. That would be like, I might as well just flagellate myself, because it would be such a miserable experience. SQL is a very complicated language. It has a lot of different nuances, and as you all know from 121, there's a lot of ways of saying the exact same thing. And so it's not really easy to translate SQL into equivalent SQL. Or I suppose you could. There's some things you can do. But in general, it's not a great level to work at. So generally what we do is we translate SQL into a plan. Ultimately, we take a couple of steps that's based on the relational algebra operations, and then we execute that with the query evaluator. So as is usual with these languages, we translate it into this thing called an abstract syntax tree. Who's heard this term abstract syntax tree before and understands what it means? Okay, so abstract syntax trees are basically just an internal in-memory representation of some program text. You can create an abstract syntax tree for a Java program. That's what the compiler does for a C program, whatever. But what we do is we take SQL and we turn it into an internal in-memory representation that our database system can then traverse and evaluate. And so NanoDB has this thing called a command, and that basically is the class that represents all commands that you can issue at the command line. And so, for example, there'll be a create table command, a drop table command. There's one to start a transaction. There's one to select data, and so forth. So there's all these different commands. And then, based on the command, it'll have different contents that you can then manipulate in memory to decide what to do with it. Now, if it's a DDL operation, the command just runs. It has an execute operation on it. You invoke execute. It does its thing. You don't actually have to implement that part because the REPL loop is already implemented for you. You don't have to do that. It's not very exciting. DML, though, is a much different beast. Now, this is a representative pipeline for processing DML operations. If you're not familiar with the term DML, it's data manipulation language, just in case you forgot. So DML operations, so that would be select, insert, update, and delete. And so you can see we take the query from the user. We parse it into an abstract syntax tree. It'll be like a select command or a delete command, and inside will be various clauses that you can then traverse, and you could even manipulate them if you want. And we go through these various steps to get to the query result. Now, the first thing to mention is that our select query gets processed into blocks that basically capture select from where. There's a few more clauses as well, but they tend to be called select from where blocks, or SFW if you read. Like, I have some optimization papers I want to give you later in the term, and a lot of them refer to select from where blocks. Okay? But there's other things that fall into these blocks as well. Group by, having, order by, what else? With clauses, if you're lucky enough to have a database with clauses. NanoDB has a concept of with clauses, but you have to implement them yourself, because I didn't do it. So anyway, but those are basically, you have these things, and imagine a query with a subquery. Like you have subqueries in the from clauses. Well, those are nested select from where blocks. If you have a subquery in the select, you say select and you have, user ID, comma, select from this other table, something based on that user ID, that's a nested select from where block in the select clause. Same thing if you have an in clause, an exists clause, or anything, any kind of subquery in a where or a having, that'll be a nested select from where block. We'll talk about how to deal with those in the future as well. Because ideally, we don't want to have query that's littered with subqueries all over it. We'd like to flatten it as much as possible. Anyway, so we have the query abstract syntax tree, and we have to turn it into an initial query plan. This is, again, a representative way that it's done, because databases certainly take different approaches. We can do optimization at the abstract syntax tree level, which is kind of a really interesting thing. IBM's DB2, I think it was DB2, but IBM had an internal database that they actually did some really cool stuff. I think it was called the Starburst Optimizer, where they actually do a whole lot of optimization at the abstract syntax tree level. And I want to give you a little bit of an introduction to that stuff, because it's really cool. Some of it is just like really sophisticated, and I'll probably give you some references later on, but it's really clever stuff. Anyway, you can also do join ordering at this level. Okay? So as you're generating this initial relational algebra plan. Now once you have that, then you can start figuring out optimizations. Are there indexes that I can take advantage of? And so forth. Do I want to use a nested loop join, or do I want to use a sort merge join? Do I have ordered data so I don't need to actually sort results and so forth? So there's things that we can do at the plan optimization phase to try to, incorporate incremental benefits or even maybe large-scale benefits as we generate our execution plan. Then finally, once the plan is all done, we've generated it, we've annotated it, we've done everything we want to it. It is basically our best guess as to a fast way to execute the query. We hand it over to the evaluation engine. The evaluation engine is very simple. It just goes through and evaluates the plan. It doesn't do any more thinking except just coordinating the generation of tuples. Okay? That's all it really has to do. Because we did all our thinking between SQL query and annotated execution plan. So the evaluation engine just does its thing. Now you'll also notice, I didn't mention this really in my discussion, but we have table statistics. The better details, the better statistics we have, the better guesses we can make as to what are good choices and bad choices, as a part of join plan, join ordering, and what algorithms to use, what alternate execution paths we have, and so forth. So table statistics factor prominently into this phase, and then obviously the evaluation engine is just accessing table data directly. Okay? So are there any questions about this sequence of steps? We're going to be breaking this up into quite a bit of detail over the next probably 3 to 4 lectures so that you get a good sense of how all these different steps work. Now, one thing that's interesting is that we do have inserts, updates, and deletes, and we do need to think about how to deal with them as well. Select is kind of obvious that it would fit into this. But think about updates. Updates are allowed to have subqueries. Updates are allowed to have subqueries with joins in them, and subqueries in those, and all kinds of things. Okay? Same thing with deletes. And inserts, we can of course have insert select. So we have all these different things that our SQL allows us to do, and we need to figure out how to handle those things. So we might as well take advantage of the same execution pipeline. So I have here insert into T1, so I select stuff. Okay, these are just really simple contrived queries, but you can see how they might work. So select A, B plus 2, C minus 5 from some other table where I want to not process all the rows, but just select a subset and so forth. So I still need a plan to generate the select results. Maybe I need to update certain rows in T1 and make sure that I only select the rows that satisfy some constraint. So how do I do that? Update T1 set A. So here I am, is this correlated evaluation? You guys already forgot what correlated evaluation is? You gonna make me cry? Or throw markers? I might throw markers instead. Yeah, unfortunately this is correlated evaluation. See, update T1 set A equals select A from T2 where T1.B equals T2.B. We have a join in here. We could do this with correlated evaluation, or we could decorrelate it. That would make it interesting. So we have some interesting things like this that we need to sort out. Delete from T1 where A equals select max A. The presumption here, of course, is that these last two subqueries are scalar subqueries. Hopefully that's obvious, but it kind of has to work that way. If these things, if the third query, let's see, if the second update, if that subquery generated multiple rows, then it should generate an error in the database evaluation. Okay? Everybody see this? Woo! All right, so those are some simple examples. So here's the observation that we can take advantage of. All four of these statements generate sets of tuples. And really the only difference is what we do with them. So if we came back here and said insert, so we have select generates tuples. What do we do with that select results? Well, we insert them into T1. What do we do with the set of tuples that's generated from the, let's say that we had select star from T1 where C in select C from T2. What do we do with that set of results? Well, we go through and we set each A's value to 5 more than it was before. And so forth. You can see how you would go through and model this as a sequence of selects to do some other thing to the set of results that you generate. So select selects tuples for display or transmission to the client. Insert selects tuples to insert into a table. Update selects tuples to modify, and then uses the set clause to figure out what to do with them. And then delete selects tuples to remove from the table. So here's how NanoDB handles this. And databases basically all do the same thing. Basically what NanoDB does is it generates a select query, and then it also has a tuple processor that corresponds to each query type. Is it an insert? Then I need to take the results and insert them into this table. Is it a delete? Well, the tuples that are generated from the select, I need to then mark deleted, and so forth. So basically, like it says here, for each tuple produced, the tuple processor does whatever with the tuple. And so there's a tuple deleter, a tuple updater, and so forth, a tuple inserter, and that'll insert tuples into the table that it's supposed to insert it to. Okay? So that makes it really easy to leverage the same processing pipeline for all these different kinds of queries. Okay, any questions? All right. So we have this, execute plan, plan node plan, tuple processor. Yeah, so there'll be something like this when you eventually get the code, which like I said, hopefully will be early this week, today or tomorrow. The evaluator also generates statistics. Remember how you had this interesting row count function that you could execute at the end of a MySQL query or operation? It would tell you how many rows were inserted, or updated, or deleted. Well, this is basically what all databases do. They keep track of that in their execution pipeline. And so if you have that value and you squirrel it away, then you can have a helpful little function that retrieves that value to let, procedural SQL look at it. Something like that. So this is basically how that'll work. The other thing that you have to keep in mind is that not all tuples are equal in this kind of model. And that becomes very important for updates, deletes, and also inserts. We'll look at this now. Basically, some tuples you generate just because you want an answer. But other tuples get generated and you intend to modify them. And so this is very important. Who has heard this term L value before? Yeah, that's about right. I expect that quite a few of you have heard about it. It's too bad that we don't have a compiler class. Or, Mike is working on an interpreters class, which some of you may not have graduated before it's ready. But L values and R values are very important in languages in general, and they happen to be important in database systems as well. Anybody tell me what an L value is? There's like the easy definition and the really accurate definition. Yeah. Yes, yeah. And an R value correspondingly, really, yeah, it should appear on the right side. So yeah, that's the, again, no offense, but that's the layman's definition, if you will, of L values and R values. L values are allowed to appear on the left hand of an assignment. R values are allowed to appear on the right hand side of an assignment. But they really can't be on the left hand side of an assignment. Okay? So you can see that when you have an assignment operation, you can have L values on the left, and you can have L values and R values on the right. Okay? Because you can read an L value just as well as you can write it. Now, what's the real definition of an L value? What's the distinction between an L value and an R value? Let's say I have a number 6. That's not an L value, right? Because I can't say 6 equals, well, not in the languages we tend to use, right? 6 equals something. But I could have a variable foo, and I can say foo equals stuff. So what's the difference between foo and 6 in my example? Ding, 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 ding. Yeah, one has an address. One has a location that I can store a value in. The other one doesn't. That's the distinction between an L value and an R value. Okay, so things like this. I kind of gave away all this. So L values are values with an associated location or address. I like that you use the term location because we tend to use location to describe where data resides on disk. We tend to use the term address when we're talking about where things reside in memory, but it's the same concept, right? I don't know why we use different terms, but we do. Okay, so R values don't have a location, so they can't be the target of an assignment. Okay, so there you go. Now you all know what L values are and R values, so if you're reading like C++ error messages and it's like, this isn't an L value, you'll be like, oh, okay, I know what that is. Okay, so we'll just wrap up real quick, different flavors. So in database systems, typically what we do is we have tuples that are backed by buffer data that is typically buffered from the disk, or we'll have tuples that exist entirely in memory. Okay? And so, for example, in NanoDB, we have this data structure that you'll get used to very quickly called a page tuple. And the page tuple basically says, this is the data file I'm from, this is the block I'm in, this is the offset in the block, and you can use that page tuple to look up and store values for that tuple. And if you modify the contents of the page tuple, and then the buffer manager goes around and eventually evicts that page, the disk data actually changes. So that can be used as the target of an assignment. You can also delete page tuples. Okay, other things contain computed values that are only stored in memory. So here's a simple example. I have username and I want to sum up the scores of that user. When you generate this grouping and aggregation, the results are not backed by disk buffers. They're just in memory. And so this is not an L value tuple. Or these are not L value tuples. NanoDB has a tuple literal object that it uses. Now, and I just want to mention as an aside that this is one way in which NanoDB deviates from general implementation, because some databases like Postgres, for example, uses buffers for everything. But and it's for good reason. It makes it very easy to write this data to disk if you need to overflow it to disk or whatever. But we don't do that because we want to be easy to understand. And tuple literals are not governed. Their memory allocation is not governed by the buffer manager. Okay, last thing to talk about. So select and insert select do not require L values. Update and delete do, because update modifies the tuple in place, and delete obviously marks the tuple as deleted. Okay, so these are the kinds of things. This, like I say, are constraints what optimizations you can apply, because you have to make sure the results that you generate are actually modifiable by the top level of the plan executor. Okay, are there any questions? Okay, so I just wanted to make sure everybody understood that. Next time we'll get into some of the exciting details of SQL translation.